Hey guys, so far we have looked at the first law of motion. We've studied about the second law of motion, few new terms like inertia, momentum, all of these. Today we'll look at the second law of motion through a different lens. We'll try to understand it differently in the sense that we will look at certain formulas that I can use to solve any sums that I might be given. Right. For us to begin, we'll start with a small activity here that for which I'm going to need these two objects. You see, a light object, a matchbox, and a heavy object, a mug. Right. So what I'm going to try to do, I'm going to use the same amount of force on both of these objects and see if there's any difference in their movement. Okay, that will be my first scenario, so watch carefully. For this matchbox, okay, I've used a small amount of force. I think I need a larger, so I'm just going to do that. Okay. If you notice, it accelerated quite quickly, right? It accelerated quite fast. That is the first observation you need to do. A light object will accelerate fast or have more velocity, either way that you want to see. Okay, I'll do this, try to put the same amount of force on this object, which is like a heavy porcelain mug. Right, if you see, its acceleration was very low. It had very little change in its speed, right? Big difference between these two objects in terms of its acceleration, right? Although the force was the same. Now, why this is happening is because whenever the mass of an object is less, the acceleration on it will be more if the force is the same, right? It's something that we looked at in the previous class also, right? So in a way of saying, the momentum is going to change depending on the force. Now, to give you another way to look at it, I will keep the mass same, but I'll change the force. Okay, we know force, mass and acceleration. So first I changed the mass of the objects, now I'm changing the force that I'm using for the objects, right? So first I'll use a mild force, like, okay, there was a mild acceleration. Now I'm going to use a little more force, more acceleration, right? It went much further and much faster also, right? So what that tells me, if the force is bigger when the mass is the same, then more the force, more will be the acceleration. I can say that force will change the momentum of an object, right? If you agree or not, think about it. For us, right now, when the object doesn't move, it has static inertia. If you remember, it has static inertia. Now, me applying force changes its inertia into dynamic, right? It gets a momentum. That is, it has a mass and it's going with some velocity. So I can tell that the momentum of an object can also change with its force, right? And obviously the momentum for that is more than the momentum for this, at least for the same force, right? So today what we'll do, we are going to look at how force and momentum can be related. For this, I'm going to direct you towards the board. So we'll be back here now. So what we just discussed is that the force is directly related to the momentum of the object, right? So if force is increasing, then I know that momentum is also increasing, right? The momentum will increase when the force increases. If the force decreases, then momentum will also decrease. But when we talk about increase and decrease here, we need to talk about it in terms of changing, right? Because every object always has momentum. Okay, if an object is at rest, I'll say his momentum is nothing but 0, right? Because m will be something, but his velocity is 0, right? So 0 into anything will be 0. Okay, so when velocity is 0, for any object the momentum is 0. But the moment we hit it and it starts to move, P won't be equal to 0, right? It will increase because V is also not equal to 0. And mass is definitely never 0, right? We know that one thing, mass for an object can never be 0. So we know for sure that since P equals to m into V, whenever the velocity increases, momentum will also increase. And we know that when the force increases, velocity also increases, just like we saw now in the activity, right? So what this tells me is the rate of change of momentum. Okay, stick with me, it's a bit long, but deal with, just stay with me here. Rate of change of momentum is directly proportional to force. Okay, we'll decode this sentence part by part, not to worry, it's very simple. Okay, now force, okay, rate of change and momentum directly proportional, 4 things that we see here. Okay, when I say directly proportional, I mean to say directly related. So what you see here is a direct proportion, right? So when force is increasing, momentum will also increase. Force decrease, momentum will also drop. Okay, so that is what directly proportional means. If one increases, the other increases. That is called direct proportion. Okay. The symbol for proportion is this. Okay. Now I am saying that force is directly proportional for rate of change of momentum. We'll look at rate of change later. First let's look at momentum. Okay, or momentum is P. Right? Now when they are saying change of momentum, for putting a symbol to change, we put a triangle. Okay. So force and is directly proportional to change in momentum. Okay. But when they say rate of, it means to say time. Okay, meaning we need to divide it with time. Okay, how much it's changing for how much time is called rate of change of momentum. Okay, so in a way, if I make this into a formula, I can write F equals to delta P, means change in momentum, divided by change in time. How much time is taken to change how much momentum will be equal to the force. If you divide these values, you get the force. Okay, it's okay if you are not able to completely follow everything. Make sure by the end you remember the formula correct. Okay. Now we know that P equals to mv, right, from here. So I can write it like this: delta of mv divided by delta t, right? P, in place of P I wrote mv because they are equal. Now what I can write this as is delta m delta v divided by delta t. Change in mass, change in velocity divided by change in time. But like we already discussed, mass does not change for an object usually, right? Usually the mass will not change. So instead of delta m, I'll simply write m. Okay, so I'll write I'm just replacing this with m, right? Like we discussed, mass usually won't change, so I'll write m delta v by delta t. All right, so this is the main formula for momentum, all right, or change in momentum. So we know what is how to find momentum. We also know how to find change in momentum. I'll write this again over there. Force equals to m delta v divided by delta t. Keep one thing in mind: when we talk about force, we say net force, right? Meaning total force of everything that is applicable. So I'll write F net over here. Okay, so this is the main formula that you'll have to remember for your numericals and sums going forward. Okay, and to state the law, rate of change of momentum is directly proportional to force, or let's call it net force. Okay, net force applied on the object means the same thing, right? I just change force to net force. Okay, if you remember this, it's very easy to come down to this if you remember the steps. If you are not able to go through with the entire process, it's perfectly okay. Make sure you remember this formula and the sentence. Okay, this is another way to talk about the second law of motion also. Alright, rate of change of momentum directly proportional to net force applied on the object. F net equals to m delta v by delta t. So this will be the end of today's class. The two main takeaways are here. Now from tomorrow and any class going forward, we'll look at any sums or anything else that we have that deal with this topic altogether. Alright, okay, thank you. I'll see you tomorrow.